Hi everyone, welcome to the sixth experiment. This experiment has two parts. The first one is a 2-bit multiplier and the second is an arithmetic logic unit. So a 2-bit multiplier is something we have already discussed. It was a part of your minor exam. This is how essentially the logic of a 2-bit multiplier would look like. Since in this case, we are designing and implementing a 2-bit multiplier using half adders and AND gates, this is how it could look like. We have two inputs, A1 A0 and B1 B0. When we multiply these 2-bit numbers, if we write down the bitwise multiplication, the understanding would become simpler. So we first basically multiply A0 and B0, right? And that multiplication operation can be represented in this case with an AND gate. Then we multiply A1 and B0. We've written that here. Then we shift the whole thing by one position. So know that this could have also been done by a shift register, but just to keep things simple, we are using just the half adders and AND gates. Essentially, after leaving this first position, what we have next is a multiplication of A0 and B1, and then multiplication of A1 and B1. In this case, multiplication can be shown easily using an AND gate, and essentially all of these individual positions have to be added up. That means the first position is taken as it is. This becomes the least significant bit of your product. Next is the outputs of these two AND gates are to be added together, and for this we could use a half adder, let us say HA1, and since it's a half adder, there would be a sum term that is actually this product, and the carry can go over to the next term. This next term, A1 B1 and this C1, they can be added using another half adder. The sum of that half adder is essentially your P2, and the carry out can then be sent directly to P3. This is how the logic circuit representation would look like. You have 4 AND gates and 2 half adders. So your least significant bit P0 is just A0 B0. Your next bit is the sum output of a half adder that takes inputs A1 B0 and A0 B1. We're just replicating this expression in the diagram and so on. So you can see that this is just a logic gate representation of this operation. This is how the code would look like. Again, in the code also, we are going to have to write at least once the half adder module. You can also reuse the half adder module that you used in the very first experiment of these labs. So when we write the module for the 2-bit multiplier, we will specify that we have two 2-bit inputs A and B, and the output of course will be a 4-bit vector. Since we have an intermediate carry, I'm bringing a wire keyword to assign variable C, and I'm just assigning everything as it is in the diagram. So P0 is simply A0 B0, that is what is written, and instantiating half adder twice and giving the inputs as they're supposed to be as per the logic diagram. You must write a test bench for this part and take at least 8 combinations. You can go through this test bench. You're already familiar with how to write a test bench. So for this experiment, you should have a timing diagram. You should also include the elaborated design. That means verification of the logic diagram that Vivado creates. So you should make sure that if you're writing a code like this, the elaborated design actually looks like this. Okay, so in this part of the experiment, again, you would have the section of elaborated design. For connections, you know that you have to take two 2-bit inputs. So you could just give input A to these two switches on RPi and input B to these two switches. You could have also used 2 of these and maybe 2 of the pink boards. It's up to you. To show the outputs, you could use these 4 LEDs on the pink board. Just please make sure that this LD3 is your most significant bit, and here LD0, this is your least significant bit of the product term. So this part of the experiment involves design, simulation, and implementation, and it also includes the elaborated design. The second part of the experiment is on arithmetic logic unit. So an arithmetic logic unit essentially performs arithmetic operations like addition, subtraction, multiplication, as well as logical operations like AND or XOR XNOR, and so on. So, since we know that ALUs are the core of all microprocessors, and in this part, uh, based on an operation code that you specify for this ALU, a specific operation, either an arithmetic operation or a logical operation, should be conducted. Right? So, basic logic operations can, of course, be implemented using combinational circuits, and that is what your code is supposed to do. So know that in this part of the experiment, you only need to do design and simulation. That means there'll be a timing diagram. And this part is for your homework. You do not need to do this in the lab, but you will have the entire week before the submission deadline to complete this part. This part should have a design source. It should have a test bench, and this part should also have an elaborated design and some comments on how that design is implemented. So if you look at the table, we could say this is the operation table or the truth table, where for a given operation code, a certain operation should be performed. For this experiment, let A and B both be 4-bit numbers. So your module essentially should have three inputs. A and B are two inputs, and the third input should be the operation code. This operation code is going to decide what operation should be done, right? So if operation code is selected as 000, the operation to be conducted is all zeros. That means your output, let that output be, say, y, right? Say that is a 4-bit number y. So that output should be set to 0000. If your operation code is 001, then addition of these two binary numbers should be done, and note that this is 4-bit addition. If it's 010, then subtraction of these 4-bit numbers should be done. If it is 11011, then bitwise AND operation should be done. Means AND of each individual bit positions. Right? That is what is called bitwise AND operation. Similarly, OR operation, XOR operation, or XNOR operation. If the operation code is 111, then output should be set to 1111. Like all four positions should be set to 1. Using this operation table, please write a design source, simulate it for each of these operations. So your test bench should include each of these operations, and then insert an elaborated design. Write your comments about the design. This part is your homework. Please note this doesn't have to be done in the lab, but can be done offline at home. Know that both these parts should be submitted together in your report. It is just that the first part is to be done in lab and the second part is an offline exercise. A video is needed for the first part because it also involves implementation. A video is not needed for the second part. Thank you.